Each substance has its own melting and boiling point. This gives some idea of the strength of the force holding the molecules in place. So there may be one type of bond holding the atoms in place in a water molecule, but another type holding these water molecules in place in the crystal. These forces are usually weaker. To help understand how this works, we'll need to look at the newly discovered biscuit atom. This is a single atom. However, this particular type of biscuit atom comes bonded in pairs as a biscuit molecule. The bond is a strong covalent icing bond. It can be broken without destroying the atom. If the molecules are shaken about, they fly and bounce in all directions. This movement is heating, and the molecules are forming a biscuit liquid. More heating, and they would become a gas. Slow down the shaking, which is the same as lowering the temperature, and gravity pulls the molecules down to the bottom of the container. The walls of the container hold the liquid in place. The molecules have a very weak force attracting them to each other. It's a very weak force, far weaker than the strength of a covalent bond. We'll use butter to show the force. The exact shape of the natural crystal structure will depend on the size of the molecules and the orientation of the bonds. If the movement of the molecules is very low, these very weak butter bonds will hold the molecules in place as a solid. Now, if we increase the shaking, which is the same as increasing the temperature, the butter bonds will break and the biscuits become a liquid again. This amount of shaking is the melting point of the biscuit crystal. The butter bonds have broken, but the covalent icing bonds are still intact. And of course, if we shook it even more, it would boil off and become a gas or vapor. The butter is still there, affecting the gas slightly.